Hello students and teachers, we are group CA04 and today we are gonna talk about a very important chapters in calculus, the derivatives. Here's our team members.
In high school, most of us were familiar with writing tangent line equations of this form. In that equations, f from x represents the slope, also known as the derivative. Why does the tangent line equations include f from x? In order to find the answers, let's consider the graph of the functions fx equal minus x squared plus 4x plus 1. We construct a secant line intersecting the curve at two distinct points, giving rise to the quantities delta x and delta y. Let x be the slope, also known as the gradient of the secant line passing through the 2 points P and Q. A remarkable phenomenon occurs as we gradually reduce the distance between the 2 points. When Q becomes arbitrarily close to P, the secant line converges to the tangent line. At this limit, the ratio delta y over delta x becomes the derivative.
We also use the tangent line equation to approximate the value of the function within a small neighborhood around the base point. Because the values of the curve in the neighborhood of x0 are almost the same as those of its tangent line, we use the linear tangent approximation at that point to simplify the computation of nearby values.
To facilitate computations, we have various differentiation rules for different types of functions. In addition, we also have higher order derivatives, which are simply the derivative of previous derivative. The differential dy represents the tiny change of y when x changes by a very small amount. Suppose an object moves according to the function x equals ft over the time interval from a to a plus h. The distance is traveled is fa plus h minus fa. The average velocity over an interval is the distance traveled divided by the time taken. However, if we consider an extremely small time interval ah approaches 0, we get the instantaneous velocity va, and that is precisely the derivative of the position function. We will move on to the applications of derivative in mathematical tools, specifically the Taylor and Maclaurin series. Below is the general formula for the Taylor series. If we substitute x equals 0, we obtain the Maclaurin series.
The main purpose of using the Taylor-Maclaurin series is to approximate a complicated function by a polynomial, making computation easier. For example, with a function sin x, the first order of the Maclaurin series introduces you a tangent line. The second order gives you curves. And the third order makes some major changes to the curves. And so it goes on with the remaining orders of the series to infinity, which adds some more details and smooth the bending, until it becomes nearly as the same as the original function. In practice, the derivative is widely applied across various fields. In this part, we will examine the following uses. Part 1. Employing the derivative to locate the extrema for material cost optimization. This application has been used by a lot of businesses to increasing their revenue. Take a cylindrical soda can for example. We have the radius and the height, and also C1 and C2 respectively, the cost coefficient for the lateral surface and the tops, with V being the volume of the soda can. We called A1 be the lateral surface area of the can and A2 be the area of the top and bottom caps. We begin by establishing the cost function. And then we take the derivative to find the critical point. Then we plug in the critical point into the second order derivative of the function, and we conclude that CR has a local minimum at R. We also have the variation table for illustrations. In conclusion, the optimal cost CR is achieved when R is equal to the local minimum. Next is the application in the autonomous vehicles. In an autonomous vehicle while driving, the control unit receives data from the sensors until it computes the solution and issues comment. But there's one important issue. The system always has a delay. When the data is received, the car is already in a new position. Therefore, the autonomous vehicle needs to predict the future position. If the system does not use prediction, it will always react slowly, which is enough time for an accident to occur. In this scenario, linear approximation is applied to rapidly predict the position within this very short time interval. We have the linear approximation equation, where delta t is small segments of time, and f'(x) is the derivative of the position, is precisely the velocity. Since the linear approximation is essentially using the current velocity to predict the future position, the equation can be rewritten like this, with vt being the velocity function with respect to time, and xt being the position function with respect to time. In order to have low error, delta t must be very small, vehicle's velocity and steering wheel must remain constant. This condition is met because the processing lag in the controller is only approximately 0.15 seconds. First, we have the controller current position at time t. Then, we must predict the vehicle's position at time t plus 0.15 seconds. Next step, we compute a decision. After 0.15 seconds, the control commands aligns with a real-time situation. Take an example. The self-driving car is currently moving in a straight line at time equals 0 with x1 equals 0 meters, v1 equals 20 meters per second. The camera detects a person crossing the road 30 meters ahead. The system lag is 0.15 seconds. The system then calculates when the command is issued, the car will be at position 3. But when the actual remaining distance when t equals 0.15 seconds is 27. Meaning that the decision to brake immediately is based on 27 meters. Thus, when t equals 0.15 seconds, the car is nearly at the position. The person crossing the road is nearly 27 meters away, and the brake command is activated at the correct time. We move to the last part, application of the derivative in road design. If a road has an elevation function hx, the road grade or the slope of the tension line at position x is the limit of delta y divided by delta x when delta x near 0, where ix greater than 0 is an uphill slope, smaller than 0 is a downhill slope, and equal to 0 is a flat road. Unit of measurement. Ix is usually expressed as the percentage, and I equal 5% mean traveling 100 meters horizontally, the elevation increases or decreases by 5 meters vertically. From this calculated road grade, we compare it with the maximum allowable grade at a standard design speed to determine if the road grade needs to be adjusted. For example, when initially designing the road, the intended design speed is set as 80 km per hour. Reviewing the standard codes, the preliminary road alignment is designed according to the terrain with the elevation function. To verify that the preliminary road design meets the standard, we must ensure that the absolute value of the road grade is less than or equal to 5%. We also have the tables of variations for the magnitude of slope. Looking at the table, we can find that the absolute value is greater than 5% for all of the x in the range of 200 to 250. So in conclusion, the design hx needs to be adjusted in that section. This is also the end of the video. Thank you for your attention.